Hello, everyone. Welcome to another session at Microsoft Zero to Hero community, Microsoft Learn community. This is Saidal, and I'm so happy to hosting another session and having another amazing speaker in our stage who is going to explore and share his invaluable knowledge with us, which is great. And we have these sessions, these live sessions every weekend, every Fridays to make sure enthusiast people, passionate people like you are following the latest update, best practices, and also those experts that we have here in our stage to be able to share their expertise and knowledge and experience with us, and we can learn more about Microsoft Cloud technology and Microsoft technology. So with that said, we have another speaker here, another live session who is going to talk about very interesting topic. I'm going to share my slides as usual. Perfect. So we have Edward today together with us to share about very interesting topic. Edward today is going to help us to discover how modern Columnstore Index in SQL Server and basically transform your analytics performance by efficiently handling massive data set with advanced comparison and fast querying techniques. So today we have a very interesting topic that we are going to learn a lot. So make sure that you are ready, and it's Friday. Next day it's holiday, and you have a lot of time to learn and also chilling about what you learned about it today. So if you haven't connected us yet, at some Microsoft Zero to Hero, at some Microsoft Hero is our handler in LinkedIn, in YouTube. So make sure that you are following us in YouTube. Make sure that you are subscribing us. Check that bell ring and make sure that you are getting latest updates from us. Beside that, if you want to share about us, hashtag Microsoft Zero to Hero and Microsoft Hero is the hashtag. Basically, you can mention us in different social media platforms. Very soon, we are going to have a transition from old-fashioned way of Microsoft Learning Rooms that we have had in Microsoft Teams to the new Microsoft Learn community rooms and also private chats. So basically, we are going to share more about that very soon. So you can be part of that big community. I'm talking about 7,000 members. So you can be part of that. Beside that, before I go for next slide, which is about Microsoft Learn community. As you know, in July, we are going to have interesting topics. So July is dedicated for .NET. So we are going to have amazing speakers, different sessions around Microsoft and also .NET and Blazor. So with that said, we have a teaser about July.NET. So let's have a look and check it out and be back soon. So yes, welcome to .NET July. Don't make sure that you register for those sessions, and also we are going to be live for those sessions in YouTube and also LinkedIn. So it's a great opportunity for everyone to be able to update, improve their knowledge, and learning more about experts that we are invited them to .NET July. So let's continue with the slides. Microsoft Learn community, you know, we have this motto. We invite all of you to follow Microsoft Learn community and make it your bookmarks. So Microsoft Learn it's the central knowledge management for every one of you. So Basically, you can get the latest updates and make sure that you can connect with the other experts in the Microsoft Learn community. And also, code of conduct. We expected you in this live session and Microsoft Zero to Hero community live session to be friendly and respectful to everyone, listen to different opinion, and kind and be patient. So with that said, I'm going to share my slides and bring Edward. Hello, Edward. Welcome to this session.
Hi, it's good to be here.
Yeah, thank you so much. And we are appreciated to have you in this stage. And basically, thank you so much that you are here sharing your valuable knowledge with learners here.
Happy to do all that. Definitely, and all the time. Great.
Amazing, amazing. Before I handed over the sessions to you, one question: why Microsoft Learn is pretty much important for everyone?
Quiz questions on a Friday. That's okay though. Microsoft Learn is a great resource. It is free. It is training on all the tools that we already use, and it's relatively authoritative. There's a lot of experts that contribute to it who are well known. So just compared to the giant mishmash of information and knowledge out there that ranges anywhere from maybe okay to pretty sketchy, this is a great one. And did I mention it's free? Which is, to me, a huge deal with any sort of documentation or training, is that it's just freely available. Anybody can contribute, add to it, or learn from it.
Yeah, that's great. And thank you so much that you pointed that to that specific part, that everyone can communicate and collaborate to increase the value of the Microsoft Learn. So perfect. Thank you so much for the answer. I'm going to bring your slides up and enjoy, people, and good luck, Edward.
All right. Well, thanks for having me here today. I'm just going to quickly start off by saying this is a fast-paced session. I have a lot of information crammed in here. I don't hold back. It's not my style. I'm going to give everything on this topic with demos and slides and pretty pictures that I cobbled together in MS Paint. I promise it'll be all the good stuff. So with that, let's just dive right on into what we're doing here. This is me. There's already been kind of an intro already. I organize a lot of events. I'm a data platform MVP. I really love doing this and being a part of this community. And with that, I'm simply going to go. It's a great time to just go, noon on a Friday. So what are we going to do here? We're going to talk briefly about analytic data and what we can do with it. Talk briefly about Columnstore indexes and what they are. And then dive right into how to make the best use out of them, best practices, guidelines, how to maintain them, and what the future of it will look like. How are we going to be storing data? So the presentation uses SQL Server 2022. But since 2025 is in public preview, I will talk about a few new things as well for fun. Keep in mind that everything here will be shared afterwards. Do not feel the need to screen capture every slide or copy down code or whatever. That's not necessary. It will all be shared later, I promise, the code and the slides. So really the beginning point for this whole question is going to be, what do we do with our analytic data? And there are a lot of places to put it. And depending on what you're doing with that data, they're great places. You can throw it in Cosmos DB, unstructured. You can put it into a data warehouse, like in Fabric or Azure Data Warehouse. You can put it into just files if you want to store it in files, like Parquet files. You can put it directly into services, Microsoft services, third-party services. You name it. You can build your own service to store your data. You can do so many things. And one of the kind of recurring themes over the year was always to never put your analytic data into a relational database, into a transactional database. And we kind of always say, separate the analytic and the transactional. That's great when you can do it. You can't always do it, though. And sometimes there's a huge reason to store analytic data alongside your transactional data or nearby. Sometimes it may simply be I have licenses already. Or it may be that I want the analytic data right there available to an application so they can report off it super fast whenever they want. And so this entire presentation is going to answer the question, what if we want analytic data near our transactional data in SQL Server or an Azure SQL database? So comes Columnstore Indexes. If you're familiar with the Microsoft Data Platform already, or any database, you're probably familiar with the idea of indexing. Query is slow, you add an index on certain columns, and now it's fast. Indexes give you structures that search through based on column orders, and things get faster. But Columnstore indexes are a little different. These aren't built for seeking out a small number of rows that we need. It's meant to take a large amount of analytic data and make it compact enough that you can read it analyze it, and do all those things quickly. So this is fundamentally a structure built for large amounts of data, millions, billions of rows. If you're talking about 100 rows, 1,000 rows, half a meg, this isn't what you want. And the technology underlying it has been used in many other places on the Microsoft data platform previously, like Excel and Power Pivot all the way through analysis services and Power BI and more. If you've used Parquet before, stored data in Parquet files, the structure is surprisingly similar underneath to what a Parquet file looks like. This is a mature feature. It was introduced over 10 years ago. It's mature. It's well maintained. And every new version of SQL Server, every year that passes in Azure SQL Database, new things are being added, which is huge. We love using features that are well maintained. And the result of all this is we can take our analytic data and store it in tables in SQL Server efficiently. And when people talk about compression ratios of 20 to 1, 30 to 1, speed boosts of 100x, 50x, those aren't exaggerations. They're not sarcasm. They're real if you do this right. So really the key to it is the name Columnstore Index makes it sound like index, but it's not. Much, much more than that. So why are they amazing? The first chunk of this presentation is going to be on why are these things amazing? What makes them special? What makes them tick? Why are they great? The number one thing is compression more than anything else. The reality here is that a Columnstore index is stored fundamentally differently than your classic clustered, non-clustered rowstore indexes. Rowstore indexes are all stored in binary trees, and they're all optimized for you to go out and grab a small number of rows at once. I have to grab 10 sales orders, 3 accounts, 20 line items. Those are the sorts of things you go out to a non-clustered index for, or maybe a clustered index. But this is not what this is all about. We want to take data that we're going to be crunching in large amounts. We're going to group by columns, because realistically, most analytic processes aren't going to grab 100 columns at once. They're going to filter and aggregate and grab some, usually a minority of them. And so the compression that goes on to this is very, very aggressive. Think page compression, but 100 times more aggressive. It uses many different algorithms. Some you may be familiar with. Some may be new to you, like dictionary compression, run length encoding, bit packing. There's other ones as well. If you have repetitive data, the compression ratios get better and better and better. And realistically, analytic data is repetitive, right? You have a column for account type, and there's 5 choices, and you have a billion rows. Well, if I have a billion rows and 5 choices, things are getting repeated a lot. Statuses and types and even just numbers and money compress wonderfully, because in general, they're either bound by small ranges, relatively small ranges, or repetitive values. And as a huge bonus here, if you know SQL Server already, the data will stay compressed until you need it, including in memory. And so you have this data, it's super, super compressed in storage, and we read it into memory compressed, and it stays tiny. So you save storage, you save I/O, you save memory, and all of that is wonderful, allowing you to cram far more data into one place and read it far faster than you would have otherwise. So I'm gonna have a lot of demos here, because demos are fun, they're exciting. All these tables have been created already because nobody wants to sit and wait and watch me build tables on a live stream. It's a waste of time. So I have many tables I've built here for demo purposes. This first one is a classic table with just a clustered index, a bunch of data in it. I insert like 23 million rows into it. I put a non-clustered on date to simulate, hey, if I want to filter by date, I can do that. And if I go ahead and I query, it takes a moment and it returns some basic information. I have 23.1 million rows that span like 4 years of data, and it took me like 50,000 reads to get all that data. But it wasn't too slow, right? I'm then going to take a table and just use classic page compression. This is the out-of-the-box SQL Server page compression. Same exact table, no difference except data compression equals page. That's it. I insert all my data. Again, I've already done all this because you don't want to sit and watch me do that now. That would be boring. Same index on order date key, because nobody really wants to. We're going to be searching by date very often. Very often, analytic data filters on date. So I do the same thing. And then our last table here, this is the new stuff. This is the Columnstore index, a clustered Columnstore index. And so I'm going to create the same exact table. But on this one, I'm going to insert all my data and then create the clustered Columnstore index on it. Done. We can now go back and check again and see what we have. Notice that query ran a lot faster, by the way. Same amount of rows, same details. Note that the reads are a lot lower, though we'll talk more about what these numbers mean later. I'm also going to run a query that's going to, just trust me, it works, but I'm going to run a query that's going to grab the space used for each table. And if I do that, I can see that I took about 5 megs plus a little bit of indexing space here for the first table, so 5 megs. When I page compressed it, it went down to about 2 megs. But when I column stored it, it went down to 340 megs. You see kilobytes per row is, a 15th to a 20th of what it was before. This is just the beginning. We're just diving in now, but I wanted to demonstrate right up front what this looks like and what the compression really means. It's easy to say things compress well. We all talk about things like this. It's nebulous, it's ambiguous, but I want to really go right up front and say, here are the savings right here. I'm showing them to you. I'm not making this up, I promise. What else makes Columnstore amazing? This is another thing that differs from our traditional tables and indexes. In traditional tables that you have in SQL, there are statistics on them. Statistics tell us basic information about the values in the table, but they're not accurate. They're not precise. They're not exactly what's in the table. They're estimates, and they fall out of date over time. And you can update your stats and things like that. There's auto update and so on and so forth. But at the end of the day, those stats aren't precise. They're close enough for the optimizer to make decisions. In Columnstore, the metadata stored about the tables and their contents is accurate. So when you compress this data, stats are built for it, and those stats are 100% accurate and they're maintained. So things like the number of rows in a table, the min value, the max value, what about nulls? All of that is in there and it's accurate. So when SQL has to make decisions about how to use this data, there's no need to scan everything. You don't need to use estimates. It knows precisely what is in the table, and that is really awesome. And Microsoft provides a whole wealth of dynamic management views that show you what's inside of the tables as well and what that metadata looks like. So if you want to know what this stuff is, it's there for you. And I'll demonstrate some of those views as well. I'll show those so many times. I have a special demo for it. We'll dive into that momentarily. Another cool thing that happens under the covers, and it's something that you don't really see, but you can demonstrate that it works and that it happens and it's good, is batch execution. So normally, when you're processing data in transactional tables, small numbers of rows, clustered, non-clustered indexes, SQL Server is built to process rows one at a time. And that sounds slow, but fundamentally it's fine because we're only really ever grabbing small numbers of rows from a transactional table, the 5 orders, the 30 accounts, the 100 line items, things like that. You may ask for more, but in general, one at a time for moving rows around operators in the execution plan is ideal. In the world of Columnstore, though, row counts aren't small. They're big. We're talking about getting counts from tens of millions of rows, hundreds, millions, billions, whatever, lots and lots of rows. So what batch execution does is it will say that as we're passing rows through all the operators in our execution plan, they'll do them in chunks. So instead of one at a time, it does it in chunks. This will not change the numbers of IOs you do. This will not impact anything like that, but it will make the query run faster. It'll process faster and finish sooner. Therefore, locks and blocking and CPU memory is held for less time. Those are all good things. This is automatic. It's something you don't have to do anything for, and you can verify it in the execution plan. And I'll show that right now for fun, because again, live demo is a blast. So I ran a query here just to show some basics, count star from a table, and dates and so on. I have a filter here, though. Give me the number of rows, a min and a max for just like 4 months of data. And so we do that, and I can turn on the execution plan, and I can look at that, and I can see that when I go over here, it says Columnstore index scan, and don't fear, this is not an index scan in the traditional sense. Whenever you read Columnstore, it just says scan because you're scanning the fundamental structures underneath it. This is okay, though. If I hover over it, it shows under the actual and estimated execution mode batch. So I didn't do anything special here. I simply ran a query. It was against the Columnstore index, and it automatically, behind the scenes, made it so that every operator here passes the data right up to the end in chunks in batches and hundreds of rows at a time instead of one at a time. This will make things execute fast. You can turn this off, you can mess around, you can prove that this is a beautiful feature that speeds things up. I'm not going to do all that right now. I'm really just showing that this is here. It's a cool feature. This is a many-dimensional feature, Columnstore Indexes, and we're going to dive into many of those dimensions today. I've talked a bit about reading data, but it's not just reading that is faster, the writing is faster too, significantly faster. One of the things that makes everything slow when inserting data into tables is waiting for it to log the transaction. If I insert 1 million rows, you've got to wait while 1 million rows worth of stuff is logged in the transaction log. And then your transaction log grows, your transaction log backups take longer, things like that. None of that is awesome when you're in the analytic world, because you're going to always be loading lots of data and nobody wants to wait for it. This is an automatic feature. When you insert large amounts of data into a Columnstore index, it will automatically use a minimally logged bulk load process. This means that the transaction is minimally logged. It won't log everything. It makes the insert much, much faster, and it makes perfect sense for analytic data loads, because typically, if you're loading data into a data warehouse or a data lake or anything like that, and it fails or something goes wrong, you just try again, right? You just start all over and do it again. That's just how these things work. You're not going to fret about the lost data. You just do it again because the data is recreatable. That's the beauty of analytic data. And so when you insert more than 102,400 rows at one time, it will bulk load. It will be super fast. It will make a huge difference. You can test it very easily. Try to insert 102,399 rows, and your transaction log for that transaction will be big. Insert one more row in a single insert, and it'll be small. The big takeaway from this, too, is that you want to insert a lot of rows at once. The fundamental advice for transactional data is batch it, make it small, avoid blocking, avoid locking. Be gentle to your transactional database. But in the world of analytics, don't be gentle. It's built for this. Insert your millions of rows at a time. It'll be happy. It'll be fast. It'll be way faster than if you decide to do it in batches of like 1,000 at a time. One note, and I'll mention this again later, an update may be a delete plus an insert. That is fun. That's what an update is. But in reality, for a Columnstore index, an update is not a delete plus an insert. If you use an update statement, it needs to manage those as a single transaction and will not be able to bulk load. So just keep in mind that bulk loading is for large inserts. That's what it's built for. Insert a mountain of data into a Columnstore index. It's super fast. Update a large number of rows. It won't play as nicely. Just a worthwhile warning to give, because it's often a misconception that's all the same, but it isn't. Let's talk a bit about what the architecture is for Columnstore indexes. What do they look like? If you would actually look at them and see how they're stored, how do they work? And this is completely different from transactional rowstore indexes. So the way Columnstore works is that your rows are subdivided into row groups. We have row groups, and each one can have to 2 to the 20th rows. Sounds a little arbitrary, but it's a good number. It's a good size number. The number of row groups will simply be based on however many is needed to cover your whole table. It could be 5, it could be 10, it could be 1 million, all based on how much data you have. Within each row group, the table is broken down into segments. A segment is the data for one column within that row group. So each column is stored separately, and each column's data is stored separately with each row group. And so each of these little squares you see here in a different row group and different color is called a segment. And so for every Columnstore index, the number of segments will be the number of row groups times the number of columns. That's it. If you have 100 columns and 100 row groups, that's 10,000 segments done. Here in this little example here on the slide, it's 6 columns for row groups, therefore it's 24 segments. Each segment is compressed separately. That means that each one can benefit from different compression algorithms that are optimized for that specific data in that segment. So if you have one segment that contains some string data, one has some dates, one has some decimals, one has some binary data, they're all going to compress differently. And that's good. You want that. You don't want it all being jumbled together. Page compression is great for transactional data, but it's also jumbling together all different data types, which is fine there, but it's not really as effective here. This is the perfect way to store data in the Columnstore world. So I mentioned metadata earlier. Metadata is stored, and again, you can look up all of these system views that tell you all about how your Columnstore data is stored. It's 100% transparent. Nothing is hidden. It's in every edition of SQL Server just waiting for you. So the first one here is a view for Columnstore row groups. I joined a bunch of other views, tables, no point in like digging into the nitty-gritty here, but the point is though, I run this and I can see that index we built earlier has a total of 23 row groups. They all have row group numbers, they're compressed. You can see the number of rows in each row groups and the size of bytes. These are accurate numbers, they're not estimates. They're 100% accurate down to the byte. This is exactly what is in each segment in this row, in each row group, all combined together. So you can say like, all right, each row group here is this big. If you add them all up, you know how big your Columnstore index is. Done. How about segments? I can go down to the detail. Again, it's actually pretty well named, sys.columnstore segments. Beautiful. I know exactly what it is. I run this and I can see details in each segment. I can see which column it applies to for all the different columns in the table. I can see a little bit of information about the compression. I have sessions about compression that dive into more detail than you may ever want to know. Feel free to look those up. They're a lot of fun. And then we can see even more nitty-gritty about how big is each segment in storage. Are there nulls? What's the min and max data ID? And if there are numbers, the numbers are here. If they're not numbers, it'll have lookup values that signify what those values will be in a dictionary or somewhere else. So you can get nitty-gritty detail here for all 437 segments in this index. Wow, that's cool. And so mountains of metadata waiting for you here, and all you have to do is just query it, and it's there for you. It's very, very straightforward. It's beautiful, and it's all relatively easy to use. You can steal my queries and use them, or use other queries that are provided by Microsoft or other contributors. How about inserting data? So we can see why the data stores and compresses well, but how about storing data? One of the challenges of any column store structure anywhere is that compressing data is expensive. It's wonderful for storage and reading, but the actual act of compressing it is super expensive. It costs CPU, it costs time, it takes effort. So underneath the Columnstore index are a few structures that are added to help minimize the number of times you have to decompress, make changes, and recompress. The more you can do that, the better. We assume that your Columnstore index will be big. It's going to have tens, hundreds of millions of rows or more. It's going to be giant. But at any one point in time, the data you're adding to it will be kind of small. It might not be tiny, but it'll be smallish. You'll have data that's big enough to bulk insert, like we showed earlier, or you'll have a little bit more. For the little bit more, you have what's called the delta store. The delta store is a straight up B-tree classic index, not a Columnstore index. It's just meant for speed. And so if you're trickle inserting smaller numbers of rows into your Columnstore index, instead of decompressing all the segments, you just decompress and updating all that metadata and then recompressing everything for all the affected segments. Instead, it'll put the small number of rows into the delta store, just this classic clustered index structure. And then asynchronously, SQL Server will move that data into the Columnstore index in a background process whenever it's convenient. So you don't have to do anything here. It's automatic, which is beautiful. You have, a billion rows in a Columnstore index, and I insert 1,000. I don't want to wait forever for it to do all that work. But on the flip side, if I'm reading the Columnstore index, reading 1,000 rows in the delta store, it's not a lot of work compared to the billions of rows that could be in the Columnstore index. And so it's intentionally meant to be fast and dirty and simple and straightforward. And then all the management of it in the background is left to SQL Server to asynchronously push it in, decompress, recompress, and do that work when it's makes sense. That way, if I were to insert one row at a time 1,000,000 times, it's not going to go ahead and waste my time decompressing, recompressing 1,000,000 times. He'll just throw those rows in the delta store and then periodically move them into the compressed row groups, in bunches, which is better. So kind of the insert guidance that I'll fall back on and just mention again, because it's very important based on that, is that if you insert less than 102,400 rows, it goes in the delta store, waits there, and then SQL Server manages in the background and pushes the data over whenever it's convenient. And by the way, I mentioned SQL Server a lot. This all applies to Azure SQL Database as well. If you're in Azure, it's exactly the same. It really is. Therefore, based on all of this information here, you want to insert large batches of at least millions of rows. There's no downside. Batching and other transactional tricks, no reason. The more data you insert at once, the better. Bulk inserting is beautiful. How about deleting? Deleting similarly suffers the same problem, right? If I had to go ahead and delete 1,000 rows and then go in and wait while it decompresses, makes changes, recompresses, I'd be here all day. I don't want to be here all day. And so what happens here is that data isn't actually deleted from a column store index when you delete it. What actually happens is soft deleted. There is a structure called a delete bitmap, which is created whenever we delete rows, and it will flag rows as deleted. That's it. So it's a soft delete. And whenever you read from the column store index, it will check to see are there any deleted rows, and if there are, it'll exclude them from the read operations. And this may sound messy, but again, the column store index is presumed to be large, really, really large. And the number of deleted rows will tend to be small. And even if they aren't, there are all sorts of processes that take care of this. If you have SQL Server 2022 or later, or you're an Azure SQL database, deleted rows are managed automatically in the background. You don't even worry about them anymore. If you have earlier versions, index maintenance can take care of it as well. So frequent delete operations can cause fragmentation in older versions, but this is pretty much all auto-fixed in newer versions and in Azure, which is wonderful. Again, you don't have to worry about anything. It just deals with it for you. So we take our previous diagram and we add in what's called delete bitmap. Once you've deleted rows, it's created, and it's simply a whole bunch of ones and zeros, saying is the row deleted or not. That's it. And so it'll overlay the row groups that are impacted by deleted rows, telling us which ones are deleted. That's it. So it'll then exclude them when you read. That's it. Done. And when no more deleted rows exist, the delete bitmap goes away. It's a really straightforward structure. It's simple. It's super fast. And again, it's built to avoid the need to keep decompressing and recompressing data, which is expensive. This is a wonderful way. So again, you delete a billion rows, well, not a billion, but if you delete a million rows at one time, it'll be fast. You wouldn't think it's fast. If you're used to transactional data, deleting a million rows could be painful, but here it's not. Because again, it's not a fully logged transaction. It's just updating the delete bitmap, and then it'll make more changes later and deal with that separately, and those will get logged. So how do deletes look? Well, we can go in here and look at all this stuff for our row groups and see what it looks like. And I can see right up front here how many deleted rows are in there. It tracks that. How many deleted rows are flagged in delete bitmap? And the answer right now is 0. I have no deleted rows. Cool. And this over here is just giving me the additional structures for delete bitmaps, delta store, that sort of thing. Let's say I go in here and I delete 100 rows. Go. It finishes pretty fast. Nice. And I go back and I run the same query from before, giving me all this information on partitions and stuff. And I can see now that I deleted rows from 3 different row groups, 4, 85 from here, 5 from here, 5 from here, 5 from here, and I can see that I deleted 100 in total, and those deletes are demarcated in delete bitmap. That's it. And I have the full physical detail of what partition it's on and where it's located. So not only can I see the rows are soft deleted, but I can very easily get insight through the metadata into how many rows are deleted and where they're deleted. This is just useful information. It's great. It's wonderful. The transparency is excellent. And very few products provide this kind of transparency to you. You can just go in and query and get it at your leisure. How about updates? I mentioned this briefly earlier, and I'll mention it again because it is worthy of a warning. Update operations are a delete followed by an insert, but in the analytic data world, because of that, you have to do it all as part of one transaction. One thing about Columnstore that makes it nice is that it still is applied with all the rules of ACID, atomic, consistent, isolated, and durable. And so transactions still apply in the classic sense. So the same way that all of your transactional operations are bound by all the properties that make a relational transactional database awesome, so are your column store operations, are all bound by the same thing. Therefore, we can't minimally log a transaction that has deletes in it as well. We just can't. It's not possible. Too many assumptions are involved. What if I update, insert, delete the same row or things like that? What do I do? And so, therefore, what will end up happening is it will delete the rows first and then do a delta store insert afterwards, which is fully logged and slow. So it won't benefit from bulk loading, and it can cause fragmentation, which I'll talk about more soon by reordering your data. Order is huge in analytic data. You want analytic data to be ordered by some key column. We'll talk more about that soon. The real takeaway from this is avoid updates. That's all. If you have updates in your legacy code, or you have it in your code, just replace it by a delete and insert. It sounds silly, but it'll make it super fast and you'll be happy. That's all. Easy fix, no big deal. And we can demo this as well. I can go in here now and take a look once again at my data, and I can see my deleted rows from earlier. There they are, there's 100 of them, and where they are. I can now go in and update 5 rows and change their quantity. Done. It was fast enough because I didn't really update a lot of rows, but I can now go back in and see what happened though. And what I see here is a whole lot more stuff here. And there's no bulk insert, there's no beautiful compressed row groups. What I see is delete bitmap for the delete portion of the update, and then delta store for the other 5 inserts. And so it did the delete insert separately, and it was all fully logged. So keep in mind that update is not delete plus insert. Just don't update ever on Columnstore, you'll be happier. Just, it's a great warning, it's a nice best practice, and it kind of mimics the idea behind a data warehouse where you don't go and update mountains of data. You stage your data, you insert it, and if you need to, you delete it, but you don't go and updating everything. It's just not really typically what you do in a data warehouse, data lake style environment. All right, this is a big best practice, and anywhere that you store analytic data on the planet, this is a best practice. Whether you manage it or they manage it or someone else manages it, it's critical. Ordered data is key to both compression and speed of querying. Ordered data will compress better than unordered data. It's just simply natural that data that is close in time to other data will be more similar and compress better. You know, all of my sales or marketing or customer data, whatever, all my data from today is more similar to data from yesterday than it was from data a month ago or a year ago or 10 years ago. Therefore, if you order your data by date, almost always the most common ordering column will be date or date time. You will see better compression ratios by a significant amount. And as a bonus, when you read your data, there's a lot of magic that can omit the row groups that don't have any data you need. If you have data that's old, if it's posterity data, if it's archive data, historical stuff, whatever, you don't have to really touch it again. If it's in order and perfect, you can leave it and it'll stay perfect forever. You can partition data if you want to as well, but it's just good to know that once your data is happy and in order, nothing else to do. What does ordered data do for us? It does some really amazing things called segment elimination. So this, again, this differs from your rowstore indexes and how they work. The first thing that happens here is when I query for data, remember earlier I mentioned that each segment is stored separately. Each sold separately in their own, you know, they're stored on pages in SQL Server just like everything else is, but the segments are separate structures. Therefore, if I query for only some columns, I don't read all the rest of the segments. So for example, if I were to query for columns A and B only, I would only read segments for columns A and B. Therefore, C through F are just skipped. And 2/3 of this table is skipped automatically. I don't have to do anything. This just works. So by querying less columns, they simply get skipped. Now, how about the data order scenario? If my data were ordered by a date, for example, from the beginning of my data date range to the end, and I were to then query for a sliver of dates, which is very frequent, right? I'll have data that goes back many years, and I'll simply want a quarterly report, or an annual report, or a monthly or weekly report. If I go ahead and I query for that narrow date range, odds are very good it's only going to need 1 or 2 row groups, maybe, and that's it. If my date range is encompassed in a single row group out of the whole thing, then I don't have to read the rest. It uses the metadata automatically and says, hey, metadata says the min and max values, and I know that 2 through 4 don't have a min or a max in this range, therefore I can skip them. And so in this case, by querying for a narrow date range, I can see that I read 6 segments instead of 24, omitting 3/4 of the data. Of course, the best possible scenario is you combine these. Now remember, an actual Columnstore index could have 100 columns, 50 columns, who knows how many columns, and who knows how many rows, billions? And so the difference is huge. If I were to query my little sample here for only columns A and B and for a very narrow date range, I am now simply getting columns A and B for my narrow date range, and I'm only reading 2 segments. That's nothing. And this is very typical. You'll have a Columnstore index that has thousands or millions of segments, And your analytic query only needs to read 50 of them or 100 or 500 of them. And that's amazing. Super efficiency right there. And I love demos, so we'll demo this as well, because why not? So I'm going to go back and run a query that we ran earlier for one specific column, the order date key. This is the date that the order was created. This is like a key dimension, right? And now the date isn't stored as a date in here. They use a min and a max data ID to encode the date to make it easier to process and do math on. But each of these numbers stands for a date. They are in order. A smaller number is earlier, a large number is later. And what I immediately note here in my data for the date key is that they're all the same. Right up to the end, the max data ID is the same, and the min data ID is the same, except for the last one that has slightly different, leftover data. But it's all the same, which means that every row group has a mismatch of values. There's no order at all. If I want to query for one value in this range, I've got to check every single row group in order to get the data I want, which will be slower. So let's demonstrate this quickly. I can go in here and I can run a query to grab a very typical analytic query. Give me a quantity for 1 month. Something like that is a classic analytic query, right? And I get my answer, and I go in here and the statistics IO. So back in the beginning, I turned on stats IO right up here. That tells me the IO operations by table, which is very useful. And so when I run that, it doesn't just tell me how many logical reads there were. It was a bunch. But it tells me something even more interesting, how many segment reads and how many segments skipped. By segments here, it's really referring to row groups and that kind of elimination. What it's telling me is it read every single one. I had to read all the segments for this column, and it couldn't skip any because there was no order. So let's say now I created an order table. Same deal as earlier. I created a table. I create a clustered index, a regular or clustered, classic. I insert a bunch of data, and then I swap in the clustered column store. And the idea here is I'm preserving the data order. I could reorder it later using an ordered column store index, but this is a kind of a legacy option for anybody writing older versions as well. It's just a nice option to have. The benefit, though, here now is I've created a column store index that is fully ordered by date. So I took that original index that I created on order date key, and I carried that over. The data didn't change order. I simply slapped on the column store index. The column store index has no semblance of order built in. It will put the structure on top of whatever data you tell it to, and whatever order the data is in, and it doesn't care. Order doesn't matter in a column store index at all unless you tell it to matter. Let's say I run my same query as before on my ordered index. My answer comes back even faster if that's possible. And I can note that I read one segment, and I skipped 22, meaning all the data I needed for this 1 month of stuff was in a single row group. And how many segments did I need? I needed to check quantity, that's one column, and order date key, the other column. And so that's not a lot of work at all. And you can also see that the number of reads went from like 10,000 or whatever it was before down to 35. And so an ordered set of data is much, much more efficient. And I can notice here now that my min and max data IDs scroll beautifully through my data set from the beginning to the end. I can see there's very little overlap between the mins and maxes, meaning whenever I grab a value, I don't have to read them all anymore. It'll encode my date value into a number, check the min and max, and it will only read the segments from the row groups that are needed to satisfy the query based on this metadata. So if imagine I had 10,000 row groups and all the data I needed was in 4 of them, I get to skip 9,996 of them, which greatly improves speed. Reading metadata and checking all the row group contents for what's in there takes time. I have now made it so I don't have to do any of that, which is great. Now, I mentioned the idea before, and it wasn't by accident, that order doesn't matter in column store indexes. It doesn't matter one bit. Within each row group, the row order doesn't matter. Nothing matters in terms of order inside each individual row group. So therefore, after you apply compression, before you're completely done, it encodes the data, and it'll then automatically reorder the rows. This is just an automatic thing that happens in the background. You can check and see if it happens. And what it will basically do is take the rows and reorder them in whatever order SQL Server thinks will make the compression most optimal. So we now know how to impact data order for all of our data set by ensuring that our data set is ordered before you compress it. But we can do more. By knowing that this exists, we know the data within each row group is ordered in such a way that it will have the greatest impact on compression. This is an expensive process, but it's automatic, and once done and once everything's compressed, it doesn't do it again until you rewrite the data. This is a great feature. It was added a while ago now, and it makes things faster. And I don't even demo it because it's automatic. This is an automatic feature. You don't have to do anything. It works, and that's amazing. Again, the less you have to do, the better. Now, there was a new feature added starting in 2022, and then an Azure SQL database, and then as the clustered version and a non-clustered version. This feature is improving constantly. You can have an ordered column store index where you tell it on creation to order by certain columns. Therefore, when you build the index, when you rebuild it, or you insert data, it will do the inserts and the rebuilds and the creations in an ordered fashion. So it'll do this work for you. It is worth testing. It's honestly better to do this by hand, but if you want to rely on SQL Server to do the work for you, you can, and it will do all this for you. Just test it. It's got to sort somewhere, right? Sorting is not cheap. If anybody knows data and data science, data sorting anything is one of the most expensive operations you can do in any system. And the more data you have, the more expensive the sort becomes. You've got to put that data somewhere and then play games with it to order it. And so if you're inserting a million or a lot of rows, it's got to put that data somewhere temporarily and then sort it before it inserts. So just keep in mind that this isn't a freebie, but it's really convenient. If you have the overhead, the resources, the time to load it, and you want to use ordered column store, do it. It's a great feature. It makes things faster, and it makes it so you don't have to manage data order anymore. It'll do it for you. So the pre-sorting can be really nice. Just, like all features, test before you put in production. That's all. It's nice advice to follow, right? I mentioned partitioning earlier, and it's worth mentioning, at a bigger scale here. If you've used partitioning before in any format, whether it's in SQL or somewhere else, you know what it's for. You have a mountain of data, and it's going to you can take your data and slice it up into partitions by some key column. It's probably going to be a time dimension, just like how we order our data on date time. And so you can, classic traditional partitioning may say, have one partition per year, or have one partition per month and have a sliding partition or something like that. Column store is perfect because in many analytic data sets, your new data is being updated as you insert new rows every day and you load new stuff, whether it's coming in a daily data load, like a data warehouse, or you're streaming in data from the edge. Doesn't really matter. You have your data coming in all the time being modified, but then you have older data. Older data doesn't get touched very often, right? It's sitting there, it's compressed, it's happy, and you may never touch it again except for reading it. And if that's the case, partitioning makes a lot of sense, because partition elimination can help further improve speeds and performance on your data. To keep it really fundamentally simple, each partition will include its own column store structure with its own row groups and segments, separate from each other. If you have a very, very large data set, that's perfect. You have 1 billion rows, partition it. Great idea. Have 10 partitions. Beautiful. If you have 10,000 rows, you shouldn't be using column store in the first place. If you have 10 million rows, you probably don't need to partition it, because having, tiny undersized partitions won't really help you either. The effort for checking partitions will be more than what you gain. So just keep in mind, this again is built for big data, big column store data. Let's demo what it looks like. So I'm going to go ahead, and I did all this already, add my file groups, do all the classic adding files, add file groups, create a partition function based on year, create a partition scheme on that file groups over that partition function, create a partitioned table, create a cluster index, and that makes it ordered. So partitioned and ordered. So the partition column is order date key, and the column store is ordered by order date key. So everything's ordered by date. Perfect. I throw in my pile of data, put the Columnstore index on there. All this work I'm just doing, I've done it already. Whew, that's nice. And now I just run my analytic query from earlier, get back my result, and could it be even more efficient? Yes, it can. Note it only took 24 reads to do the whole pile of work here, and that I had to read one segment and skip 2. I had 23 before, and now I've read 1 and skipped 2. That's it. And so partition elimination made my life far, far better. And this savings will apply to inserts as well. If you insert data, you won't have to go and touch every single row group. You'll only touch the ones that happen to have the data and the partitions that happen to have the data. So again, beautiful, beautiful way to take data that's big and further subdivide it and make it more efficient. Again, all this information, the slides, demos are all available later. So feel free to take whatever you want from that, ask questions later on. Contact me afterwards with more questions if you want to. So more best practice, I alluded to this one earlier. This is the best practice everywhere, not just here, but query fewer columns. The benefit here is even bigger than in transactional queries, transactional land. If you select star, but you don't need star, you're reading everything. Every column, every segment, for every row group you need, you're reading it all. But when you query only the columns you need, you skip the ones you don't, and you simply don't have to read them. If I have a data warehouse that has 60 columns, and I only need 5 of them, just read 5 columns. Don't grab star. It's a simple piece of advice because most analytic queries don't read all the data. And if they do, you probably should find out why anybody wants 50 columns in some dashboard or report or whatever. There's just no point. Maybe you're throwing AI at it, in which case, cool. You want to look at everything. But even then, focus is good in analytics. And so querying fewer columns is great advice, both fundamentally at a data architecture level for making good decisions, but also at a physical level here because you'll just read less data. And the benefits of it are far more amplified than the transactional queries, where your biggest penalty there is just having to take that data and put it in memory and then transmit it through I/O, through networks, other places, so on and so forth. There's one more bonus available, and that's Columnstore archive compression. For your data that's a little colder, that's used less often, maybe it's the posterity data, maybe it's your compliance data, but basically it's data that you read sometimes, but you're really never going to write again very often. It's cool, cold data. You can still write it once in a while, but it's more expensive. This is the extra compression. Archive compression is more aggressive compression than standard Columnstore compression. Costs more CPU, takes more time to run it and compress, but it's relatively quick to read, and it will take up less space. Therefore, less memory is used as well. You can pick this in a partition by partition basis. So if you have a massive Columnstore index with 30 partitions, you can have one partition be your active partition that you're inserting, updating, deleted from. You can then have maybe 15 partitions that are read, but not as often. And then your old partitions that are barely ever touched. And those are the ones that you archive compress because nobody writes to them anymore, and people don't read them a whole lot. So therefore, you can make them more efficient, faster. So you have more compression options if you want to get more aggressive, and there's definitely great use cases for it. So earlier on, actually jump into this. I'll show this first. When I created a table, this is the exact same sort of table as before. It's going to be a Columnstore index. I'm going to put the data in, cluster index, order it, swap in the Columnstore, with the only difference being data compression is Columnstore archive. Now, I'm going to jump back to a query from earlier and compare the table sizes for everything we've done today. So for every single table I demoed here, what are the sizes of everything? And I can go ahead and I can look at that right here and see that my largest table had a covering index. It had the extra index, which made it bigger, but it was a little faster to use a covering index. The raw table is about 5 megs. The page compressed table is like 2 gigs. They're all gigs, by the way. Sorry, not megs, they're gigs. But then I can see Columnstore brought it down to 340 megs, third of a gig. When I ordered it, it went down to 100 megs. Now, note that when I ordered my data by date, it went down to a third of the size as before because the data on nearby dates was so similar to itself that it compressed that much better. Huge difference. You may not always see this level of compression in every type of table you create, but you will see a benefit. I guarantee it. If I partition it, it doesn't get any smaller. That's not a surprise, right? It shouldn't get smaller. It should be about the same size because partitioning you don't do to save space. You do it to improve management and maintenance and maybe benefit from partition elimination. When I used archive compression, I note that it got another 25% smaller. So I went from 5 gigs of data down to 75 megs. It sounds absurd, but it's not absurd. It's completely rational. It makes sense. And this is all compression, 100%, and me putting the data in there in ways that optimizes that compression. All this is repeatable. It's easy to do. It's fun. So a few more notes before we jump to questions. Index maintenance is not as big of a deal as it used to be. If you're running Azure SQL Database or a newer version of SQL Server, so much of this is done for you, and it's beautiful. If you run an index reorg in the Columnstore world, it's very, very different than what it used to be. It's an online feature. If you have data in the Delta store, it can process it for you if you want. If you have tiny, undersized row groups that got small through deletions, it will combine them for you. And if there's deleted rows, they will get processed and deleted, and the delete bitmaps cleared out. A rebuild is bigger, more time-consuming, and harsher. Online rebuilds exist now, but that's not a feature in every edition of SQL Server. You'll recreate the index from scratch. It gets rid of all the fragmentation. It's very time-consuming. Rebuilds are very rarely necessary unless you go in and you really mess with your data and create a lot of fragmentation. If you follow best practices, you have ordered data, you don't do a lot of updates, just inserts and deletes. In general, over time, you're not going to have a huge issue. Rebuild it once in a while if you need to, but you won't have to do it often. You don't need a regular rebuild every week. Edge cases will, but majority of cases will not. Some people just simply say, I'm going to do a reorg after I load my data. Done. It's fast, convenient, online. I don't have to think about it. You can separate it by partition if you want. And again, that old data that never gets written to anymore, you don't have to do maintenance on it anymore either. So keep in mind, this is not the same level of urgency as index maintenance on a transactional database where you may need it a little more often depending on use cases. You can really go hands off here and rely on reorgs or maybe even nothing and be totally fine, especially in newer versions in Azure SQL Database. Can do non-clustereds. They provide analytics support to transactional tables. If you have a need for real-time operational processing against your transactional tables, you can create a Columnstore index. Non-clustered, column list. The order, though, you have no control over. The order is defined by your clustered row store. If it's a good order, great. If it's a bad order, too bad. So sometimes a covering index may be as good. The ideal solution, of course, everyone's going to say, separate your analytic and your transactional, right? Put your analytic data over here, put your transactional data over here. If you can do that, do that. Maybe create a separate column store structure over here for your analytic data, keep the transactional here. But again, not everybody can do that, so I totally get it. Whatever you do here, be sure to test and verify that what you're doing is faster. Non-clustered column store can provide great speed boosts for data that the order is relatively helpful for whatever queries you're running. If the order is random, if it's a identity PK, if it's disconnected from your actual analytic query order, then you may not get as much out of it. So just test, that's all. So final demos here. We can create one final table. I can put onto this is our big table from earlier. I'm going to go ahead and add a non-clustered column store index on it, on the order date key and on quantity. This is everything I need to run my analytic query. And so I'm going to go ahead and wait forever for it to run. If it takes too long, we'll just keep going. That's really no big deal. And so I'm going to separately, I've already built this table. I already have the covering index table. And so this just has a covering index. So we have our non-clustered column store being built on here, on classic row store. And then I have a special table with a covering index on it. And the covering index will simply cover my query as well. Ordered by date, include quantity, done. And so I don't want to wait for this. I should have built this earlier. That's my mistake. But what you would see if I went through and ran this, I'll run the covering index query on here. And what you'll notice is it's pretty fast because it's only a 2-column index. It's a very common query. This is fast enough to me. It's a lot of reads, but it's fast. I ran it. It finished sub-second. The non-clustered column store was also fast, but it takes up a lot more space. Again, you have to order by your PK ID, so you don't get any row group elimination, segment elimination. That's just the way it is. So those are my final demos, and I want to jump back now and wrap up for questions. I covered so much here because I wanted to really show how many features are involved here. The real big takeaway from this whole presentation, if you get nothing else, is Columnstore Indexes allow you to build analytic data in massive quantities in Azure SQL Database or SQL Server. You can manage your analytic data right there alongside other data, alongside your transactional data, and whatever else you have in there. You can have some amazing query speeds. You can greatly reduce storage and memory consumption and make everything much, much faster. It's close to set and forget in new versions in Azure SQL Database, but it's close. If you manage it optimally, you'll barely need to ever touch it again. If you have a good data order that increments naturally over time as you add new data by date and you partition it, you can basically scale it indefinitely. I've used Columnstore indexes that have hundreds of billions of rows, and they're still very, very fast. So I love pointing out this feature because it's very often overlooked, but it's a great way to store analytic data in SQL available for anybody who needs it. You can point Power BI to it, you can point reports to it, you can load the data out into Fabric or somewhere else, you can do whatever you want with it. It's there for you to use, and it's optimized for analytic speed. So I'm going to leave my information here. Feel free to find me afterwards and open it up for questions for anybody who happens to have questions. With that,
yeah, thank you so much, Edward. I'm not consider myself as a data platform engineer, but how you explain it, it was wow. So I learned a lot from you. Thanks so much, man.
thank you.
Perfect.
Thank you.
Yeah, we have several questions and some inputs. So first of all, Mehrdad asked, hi, Said and Edward. This session is one of those that we have to watch several times to digest and put the partition. Edward, would you mind sharing your scripts?
Yes, I will post them later, and I'm assuming you're going to grab them as well. Should I send them over to you afterwards to post somewhere as well?
Yeah, amazing.
All right, so they'll get posted.
Yeah, perfect. So another question from Mehrdad, does select star only impact on segment elimination?
When you select star, if your filter helps eliminate row groups, you'll still eliminate row groups, but select star simply means you're going to read data for every column. If you have 20 columns, you read 20 columns worth of data. So you still can have some segments eliminated by your filter clause if your data is ordered. So if you need all the columns, you still need them. That's life. But if you don't need them all, don't select star.
Cool. There is another question, this time from Mehdi. As data is compressed using the method, is there any benchmarking available on how fast the compression will be with different VM configurations?
How fast will it be in different configurations? So the compression here is going to be, it's proprietary algorithm for Columnstore and Columnstore Archive. I don't know of any benchmarks. There is a white paper out there. If you really have a lot of coffee on you, I read an excellent white paper on Columnstore compression and all the nitty-gritty details on it. I've done presentations on it as well. And if you're interested in that, I can point you in that direction afterwards. You could also look up Columnstore Index Compression SQL Server. You'll discover a white paper that is quite long, but will tell you everything you want to know and more, though you may want that second coffee if it's getting a little late in the day. It's a white paper, so, prepare yourself. But it's good stuff, though.
Cool. Another question from Mehrdad. Any advice on how many column store index per table?
So if you have a clustered column store, that is your one index in the table. And that's all you generally need. My recommendation for any analytic table, that's fundamentally analytic data, is create clustered column store, order it by your date, and stop right there. That is probably enough, and it'll probably be fast. If you have constant queries based on other columns, other filter clauses like an account ID or something like that, you may need to add a non-clustered row store index, maybe. But I always fundamentally recommend just the clustered column store and nothing else. You'll specify columns, the whole table is column stored, and you go from there. That's my recommendation to begin. Like 95% of use cases will be satisfied by that. Historically, every project I've worked on that used them has almost always fallen into that camp. So I recommend start there before you do anything else, and you're probably good at that point. The non-clustereds, you pick the columns. You can have more than one if you want, but the clustered only one. And again, I recommend going the clustered route whenever you can, because fundamentally analytic data benefits from a fundamentally analytic table.
Okay, cool. Question from Shamim. Do you envision AI being able to do this optimization for us in the near future?
With the right context and training, yes. I'm always hesitant to hand over to AI complicated or advanced features. And some of the things I talked about today, like data order and choosing the compression types of partitioning, are a little more advanced. I think AI in the future at some point will be able to help if there aren't built-in features to already help us with it already. So I do think eventually we'll get there. We're not there right now. And so if you do want to use Copilot or AI to help write code to manage your analytic data, just use a little bit of caution, sanity check it, make sure it's doing what you want before you do it. But at the end of the day, your number one key metric is duration, right? It's query duration. How long do analytics take? If I run a report or I run some machine learning algorithms and they complete in seconds, everyone's happy. If it takes 20 hours, people are unhappy. So use query duration, process duration as your ultimate guide as to whether you're good enough or not.
Yeah, cool. Another question from Mehdad. In what scenario would you avoid using a Columnstore index, and how would you design for hybrid workloads?
So a hybrid workload requires you to decide, is it fundamentally analytic data first with some transactional queries, or is it transactional data with some analytic queries? Now determine, do you create a clustered column store, maybe an extra row store index or two, or do you create a clustered row store with some column store non-clusters on top of it, or just simply some covering indexes? I would avoid column store for very transactional data. If you're reading and writing small numbers of rows constantly, if you're updating small numbers of rows constantly, that isn't analytic data. Build a transactional table, start with covering indexes and other features, and go from there. Only add column store if you think you need it, or it really makes you a giant speed boost. Alternatively, if you have very analytic data and you occasionally run some transactional-like queries, make it a clustered column store and go from there. Again, I like building for the 99% of the time when things work beautifully at the best practice, and then for the 1% of the time where things are a little weird, you can then go and go ahead and do a few unusual things to optimize for it. So I would stick to the straight implementation based on what kind of data you're using, and then go from there.
Okay, cool. There is no more question, just several thanks to amazing presentation that you have had here. It was a really great session. But before we wrap up the session, basically we have a rule in our community. So we ask a speaker to choose the best question. So we actually give that person a voucher of 50% discount of any type of Microsoft exam. So please select one of those best question, or select one of questions that you think it was the best, so we can announce it as the winner.
Sure. I think my personal favorite question was the last one from Merdad, where he asked, in what scenarios would you avoid using a column store index? He was brave. He went out and said, hey, when wouldn't you use this cool thing that you just advertise like heck to me for an hour? And I give a lot of credit for that question, because it puts me on the spot to really justify why we love this stuff. But also, when shouldn't you use it? When's a good time to not use the cool feature? So I appreciate that question a lot.
Yeah, I know Mehdad. He's one of the amazing person in our community, Microsoft community, and he has own also Microsoft community called, if I'm not mistaken, Fabric Cafe, and he's amazing. Since he's the community leader, I can give him a voucher. However, please select another one, because why not? We can have two winners.
Okay, sure. You asked some good questions here. Let me go ahead and pick another one. I would say that this is a great question, because everyone's asking this question. From Shamim, do you envision AI being able to do this optimization for us in the near future? It's a classic question. We all want to replace ourselves with AI, right? We all want to go to the unemployment line one day and have AI do our jobs for us. I'm kidding. But it's a worthwhile question to ask. And the great guidance is always, is it advanced or is it basic? And that's often going to be the guidance right now for, can it currently do the job for you? And how long before it will be able to in the future is how advanced is it? So great question. I do appreciate that as well. Again, when am I not needed anymore? And the answer is, I'm still needed, and you're still needed as well.
Yeah, definitely. Perfect. Then Mirdad and Shamim, we will contact you and share the discount with you. Thank you so much, everyone. Join us from different platforms, LinkedIn, YouTube, and StreamYard. Don't forget to join another session that we are having in the next week, and also make sure that you register for July.net. And thanks again, Edward, that you were here together with us and share your valuable knowledge with us, and hope to see you again on this stage very soon.
Thanks for having me, and I look forward to seeing you again somewhere, anywhere here.
Yeah, for sure. Perfect. Enjoy your weekend and take care. Bye.
You too. Have a great day.